All right, thank you. So yeah, first of all, I'd like to thank the organizers for organizing this very nice conference and giving me the opportunity to present my work here. So in this talk, I'll continue to discuss the hydrodynamics of tidal disruption events, and in particular, how the gas strip from the star actually gets channeled towards the black hole, in particular by forming an accretion disk. And also what is the associated radiation accompanying this process. So the main goal is basically to first be able to actually explain observed properties of current tidal disruption events. And in the future, we also want to actually, especially in the area of the Rubin Observatory, be able to use observations to infer parameters of the system, for example, the black hole mass. So thanks to the wonderful talks before mine, I don't have to give too much of an explanation of the motivation for this. Instead, I'll just go right into the core of the problem, which is the hydrodynamics of TDEs. So here I'll try to explain the whole picture using the results that we got, and try also to emphasize the phases that we think are the most crucial, the phases that are easier to study, and the phases that are more complicated to study. So as you may guess, the picture starts from a star that is incoming a supermassive black hole, entering the tidal radius. After that, the star gets disrupted and gets launched into a stream, half of it being bound to the black hole and returning on very eccentric orbits, while the rest gets unbound and escapes the black hole's gravity. So there are a few properties I want to highlight about this stream. The first is that the stream is actually thin in the transverse direction. Its width typically does not exceed tens of stellar radii. This is coming from work that has been done by several people in the room, such as Eric and Chris. The second property I want to highlight is that, as you heard this morning, there's a rate at which the bound mass comes back to the black hole. It typically rises after critical time T-min, after which it reaches a peak, and then at later time decreases with a T to the minus 5/3 power. So here I think it's worth emphasizing that until that point in time, actually, there hasn't been any significant observational signatures. But this phase is really well studied using analytical calculations back in the 80s, and now with more accurate simulations. The picture I just described is basically the one we think is right. However, the later phase of evolution, as soon as this stream actually reaches pericenter, is much more complicated to study, and the reason is essentially a computational issue. It's extremely difficult, actually, so far impossible with current computational facilities to resolve the stream, especially at pericenter. And this is quite unfortunate because all the observational signatures of TDEs will come from what happens after the stream comes back. So there have been several approaches to kind of overcome this computational problem. Here I'll focus on the one we studied, which consists in identifying the phases that are the most crucial for this evolution, and then study them with resolved simulations, and then try to piece them together to get an understanding of the global hydrodynamics. So this is the picture that I will describe now. So the stream passes at a distance that's not too much larger than the gravitational radius of the black hole. As a result, the stream precesses, and also, as we've heard before, at pericenter there's a strong compression of the stream causing another shock. I'll come back to this. And due to precession, the part of the stream moving out is now on a collision course with part of the stream moving inward. And if everything was to happen on the same plane, these two streams will collide. But if the black hole has a spin, then there's another precession effect that changes the orbital plane of the gas here, such that this gas still belongs to the plane of the stream, but this gas may belong to another plane, such that this collision may be prevented. In that case, there will be more windings or revolutions of the gas around the black hole until eventually a collision does occur, and I will refer to it as a self-crossing shock. So this shock dissipates a fraction of the stream's kinetic energy, launching an outflow, and this outflow will keep expanding to encompass the black hole. And as you can see from the different trajectories, this gas will interact at later times through secondary shocks or circularizing shocks, forming an accretion disk around the black hole. So these shocks may be irradiative themselves, but most importantly, they are able to form an accretion disk, and once accretion proceeds, it leads to additional X-ray radiation. So TDEs are also observable in the optical band, and in this picture, we propose that it is the reprocessing mechanism that operates. Basically, this high energy radiation diffuses out through this optically thick envelope formed from the self-causing shock, and by doing so, it gets absorbed, re-emitted several times until eventually the photons emerge in the optical band. So now I'll come back to the different phases that are involved in this process, starting from the nozzle shock at percenter, then the self-causing shock, and in the last part of the talk, I'll explain what happens later on, in particular how the accretion disk forms from the outflowing mass. Right, so starting from the nozzle shock, so as I mentioned, it's extremely difficult to resolve the passage of the stream at percenter, and the nozzle shock is basically caused by the fact that if you were to look along this direction, you would see the stream extremities being confined between two orbital planes. If this gas was made of test particles, these two test particles would cross each other. Because this is gas, there's a shock forming, which is the nozzle shock, and then the pressure rises, leading to this gas bouncing away when it's now moving away from the black hole. So our strategy to go around the resolution requirement at the nozzle shock was to study this process with 2D simulations. So considering a section of stream, initially in the red rectangle here, and follow its evolution into dimensions as it goes through the nozzle shock and then comes back on the other side of percenter in this blue rectangle here. So this is the initial condition. Initially, the gas will be compressed, and I will also mark the initial boundary of the stream in white. So as promised, I cannot launch my movie, that's too bad. Yes. Somehow when I'm in full screen, I cannot click. You know to software. It seems to play, yeah. Oh, that's not good. Just when I click on it, it doesn't do anything. Oh, that's better. All right, somehow it worked. So the stream gets compressed due to the tidal force, and then it reaches the nozzle shock, gets compressed to a very thin width, which is the fraction of the stellar radii, and afterwards the stream bounces away. This is basically the final density profile when the stream has reached this blue box here. So if I come back to the initial boundary of the stream, the main takeaway here is that even though the density profile has changed by a little bit, most of the mass is still confined inside the original boundary, such that this picture I'm drawing here with the two streams being very similar is the one we think is physically expected. So as was mentioned by Shoshan, this is a result that is actually not confirmed by 3D simulations. Could be because there's different physics of 3D effects at play. It could also be because the resolution is not high enough. But the main takeaway from our work is that there's no significant expansion from the nozzle shock, such that this picture of similar streams can be used to study the later phases of evolution. So the later phase of evolution is a self-causing shock that happens between two streams that we assume to be identical. And we studied this collision using local simulations and also working in the frame that is moving with the common tangential velocity of the two streams. So in this frame on the right, the two streams are colliding head-on, and what happens is that the kinetic energy gets dissipated, and as a result, the gas gets launched into an outflow with terminal velocity is VR, because the simulation is adiabatic. So when we boost this picture back in the lab frame, now the outflow has a velocity profile that is a combination of an expansion in blue with also a net speed towards the left. So interestingly, one can conclude from this velocity description that there's always a cone of unbound gas moving towards the left, and there's also gas moving on retrograde orbits towards the right. But the main takeaway is that the self-crossing shock launches a quasi-spherical outflow from the collision point. So we've heard a little bit about whether this self-crossing shock can actually lead to radiation if the outflow is very spherical, like we found in our simulation. Actually, the radiation efficiency that we predict would be quite low. And the reason is that, I'll go quickly on this. The reason is that the photons gets generated on small scales, similar to the width of the stream, but the photons are basically doing work on the gas to make it expand until they reach the much larger trapping radius. And so by the time the photons are able to escape, they have actually lost most of their energy. So the conclusion is that the luminosity is actually just around 5% of the heating rate, which itself is about 10 to 44 arc per second, such that the final expected luminosity would be around 10 to 42 arc per second at peak. So this is unlikely to account for most of the emission, but it could lead to some precursor, as was argued. All right, so another interesting aspect is that these collisions may be offset, and this is if the black hole has a spin. As I mentioned, these two streams, in that case, may be on different orbital planes, so they'll be offset by some offset distance, delta z. If delta z is 0, this is just the Schwarzschild case, the stream will collide as before. If delta z is larger than h, there's no collision at all, but if delta z is in between 0 and h, then there will be a collision, but it's offset. In that case, as was found by postdoc Tai Yankovic, using the same local simulations I showed before, if there's no offset, the outflow would be roughly spherical. A small offset, the outflow would be still pretty spherical, but now slightly misaligned with the equatorial plane. And in the most extreme case, where the two streams are very offset with a delta z here similar to the stream width, then the stream just graze each other, gaining a bit of energy so that they expand, but mostly their trajectories remain aligned with their initial direction. So the main takeaway is that there's some deviation from outflow sphericity due to this spin-induced offset. All right, so now I'll explain what happens next to this outflow. So to be able to carry out this global simulation, the technique we used is shown here. So you have to imagine that the stream came back following this dotted line here, processed, and then came back here where it's self-collided. And the orange color here is showing the density of the outflow, whose properties are obtained from the local simulation I showed before. And this outflow is continuously injected inside a larger computational domain. Here I have to emphasize that this is assuming that there's always a stream going around the black hole, and when gas arrives here, this stream may actually be affected by the gas already present around the black hole. So this is a limitation of our approach. So this movie hopefully will play. Okay, it also doesn't play. And I don't remember what I did before. It was like the 12th time. So oh, no. This is not the right thing to do. So this is the evolution of the outflowing gas that forms this large-scale envelope, and due to circularizing shocks, a disk promptly forms around the black hole. And now I have another movie, so hopefully this one will work better. I think I just have to keep clicking until it works, basically. I don't know why it doesn't work. Okay, I'll show it on the... I cannot actually share my screen without... Okay. Yeah. Oh, okay. So that's the evolution. The radiation energy gets produced by the exact same shocks that form the disk. It shows up in orange here, in yellow. And then this radiation diffuses out due to radiative diffusion to irradiate the surrounding gas. Interestingly, except in this region around the self-crossing shock that is screened of radiation. That was the last movie, so the rest should be fine. So here the main takeaway is that we observe a rapid formation of an accretion disk, and radiation from the circularizing shock responsible for this formation irradiate the surrounding envelope. Right, so we can also compute the bolometric luminosity, is shown in black here as a function of time. And basically, as soon as the first shocks take place, the luminosity increases to about 10 to 44 arc per second. Encouragingly, this is enough to account for most observations. And in contrast to the self-crossing shock, these circularizing shocks are very relatively efficient, and this can be seen by looking at the black line that is only slightly smaller than the gray dashed line representing the heating rate. Now, another question relates to what kind of spectrum we can expect from this disk formation. So this is a question that we cannot answer directly from our simulation because all the quantities are frequency averaged. But we can think about it in terms of the radiation temperature of the disk, which is around 10 to the 5 Kelvin. So if this disk was to emit as a black body, the black body would peak in the extreme UV band. However, this black body emission does not reach us directly. It has to go through this large-scale envelope that's optically thick. And we think that especially due to the presence of this cold spot here, where the bound-free opacity will be enhanced, this EUV radiation will be absorbed and re-emitted in the optical band. So this is a mechanism that still needs to be confirmed with multi-frequency relative transfer calculation, but it's the first time that a mechanism is proposed based on first principles simulations. All right, so I think I'll just give my takeaways. I'm not too late. That's good. So the first takeaway is that using this 2D approach to study the nodal shock, we do not observe a significant net expansion of the stream. The self-crossing shock involving two identical streams is launching a large-scale outflow, but it's not relatively efficient. And we observed using this injection technique I described a rapid formation of an accretion disk, and the secondary shocks are radiative and lead to a luminosity that can account for observations that is around 10 to the 4 T4 arc per second. And finally, we propose this reprocessing picture using especially the cold spot region in our simulation to lead to the optical emission detected from tidal eruption events. So I think that's the last slide. I just want to conclude by saying that this approach, I hope, will pave the way to a robust paradigm for tidal eruption events, understanding how the emission depends on the system parameters that will first allow us to understand observations better and hopefully use them in the era of the Rubin Observatory to actually infer properties of the system, black hole mass, and in the future also black hole spin and stellar properties. Thank you.
Questions? While we're waiting, so your conclusion about the first self-intersection shock producing less than twiddles 10 to the 42 ergs per second. Is there any variation on that number as a function of the various parameters of the TDE, beta, for example?
Oh, beta. So in terms of black hole mass, I will choose black hole mass. But basically, there's if if you change the black hole mass or increase beta, then the self-crossing shock will happen closer to the black hole. And so this will increase the healing rate. If you consider the black hole mass, but yeah, as I mentioned, the heating rate will be reduced due to adiabatic losses.
Yeah.
If beta changes, I don't think adiabatic losses will be the same because the fallback rate does not depend on beta. Mm-hmm. But if the black hole mass changes, the fallback rate will, if the black hole mass increases, the fallback rate will decrease. So that will lead to less adiabatic losses, so slightly increase the emerging luminosity. I think analytically you can show that accounting for both of these effects, the emerging luminosity goes like black hole mass to the 1/6 power. So it's a pretty
interesting. Okay. Thanks.
So about the self-crossing with the offset, creating asymmetry in the ejecta. So would that help enhance the radiation conversion by having directions where radiation can preferentially escape?
Yeah, I think so. That's something we mentioned in the paper. Oh, no, that's not this. So indeed, one might expect, for example, in this case, that radiation can actually diffuse more easily because now there's all this space that's basically very low density. But actually, there's another effect that's competing this, which is that actually the density is larger. So why, in that case, there will be diffusion also in this transverse direction, kind of the photons escaping in the faces of this cone. But it turns out the adiabatic losses are not reduced by this effect because there's the kind of competing effect of increasing the density.
Thank you.
So I have another question that's kind of related to this. So in these simulations of the self-intersection shocks, are you assuming that the densities of these streams are the same as they're coming and intersecting, or are you accounting for the fact that at early times, the earliest material will have a lower density and that sort of thing?
So we assume that the streams are identical, including their density is the same. And this assumption, if I come back to that part, this assumption neglects the fact that basically this part of the stream comes from a different part of the star than this part of the stream. So this assumption is actually, it's correct if the kind of time difference, times of arrival between the two streams is very small. So it will be more correct if the streams intersect close to the black hole. But indeed, if they intersect near apocenter, the time difference between the two will be over the T-min, and so in that case, it may be significant. The outflow may not be as spherical.
Yeah, thanks. So did you see, or in your simulations, did you consider what happens? I'm assuming the simulations are basically done where the self-crossing shock happens basically on the first stream, right? But you mentioned that it could have happened after several F-saddle precessions. Yeah. Have you considered if the simulations change if you take a self-crossing shock from much later in the sort of evolution? And then do you expect the streams to change significantly after going through the nozzle shock a few more times?
So to answer the first question, we did not check this, but there's a good reason. And basically, the reason is that even when there are all these windings, actually the collision still happens between two successive windings. So it is actually quite similar to the case where it would happen after just zero winding directly. And the second question, the effect of the multiple nozzle shocks, I think is a very good question. Indeed, it's possible that one nozzle shock may not affect the density that much, but when the stream comes back and experiences several nozzle shocks, it is definitely possible that the effect is more important. It's something that I want to study.
Awesome. Thanks.
Any more questions? Okay, let's thank Clement again.